Well, hello and welcome. So what are we doing today? So first of all, just a couple reminders that there's a homework due Sunday, and we only have, about 2 weeks left in the semester, so it's time to start thinking about the final exam. So the final exam, just make sure you have it on your calendar. It's Monday, May 4th in the math block at 9 to noon. And I'm expecting to still keep it that way. And we'll probably do a process very similar to what you just did on exam 2 and 3. Uh, and yeah, other than that, do you guys have any questions before we get started? All right, so before the exam, we didn't get to quite finish 4.2. So we're going to try to finish up 4.2. So let me try to remind you of what the main ideas we've learned in 4.2 kind of up till now. So the main idea was we learned that there's this new symbol called the definite integral, and if we put a function in here, all right, so like the definite integral is like this part, and then you can put stuff in the blank here. You can put different functions in here, and if you put some generic function f of x, then what this really calculates is the signed area. A lot of times we omit the word signed, but that's what we really mean. So this is an area under the function f over the interval a to b. Right, so kind of the picture you should have in your head is whenever you're calculating an integral, you're really calculating an area. So if you have some function f, some interval a to b, then it's whatever that area is. So, and it's the exact area. So this version is the exact area. We're not doing any approximations this time. So it's whatever this area would be exactly. Okay, and we learned that the way it's defined is the definition is essentially that if you chop your interval into n rectangles, let me just sort of, let's just write it the generic way. So this part would be, this would be an approximation using n rectangles. And then to get a better approximation, we make the number of rectangles bigger and bigger. And to get the exact area, we send the limit off to infinity. Okay. And so this is the version we're going to stick to. So this part here comes from right endpoints. So we're always going to use right endpoints when we do this sort of thing. Okay. So I asked you to write this down on the exam. I didn't expect you to be able to calculate it quite yet. But that's kind of what we're going to get to today. So let's see an example of an area that's not obvious to calculate it, geometrically. It's not a nice shape. So we might have an example like this. So let's compute the definite integral. Definite 0 to 3 of something like we'll stick to x squared minus 6x. And so basically what you would do is you would write down the definition. So in the definition, what things do you need? You need your delta x, and then you need your right endpoints, right? So let's figure out what those are here. So for us here, delta x will be the length of our interval. And so remember, the interval always goes from the bottom number to the top number. So it'll be 3 minus 0 over, and here we just write it for generic n. So delta x is 3 over n. And then right endpoints are, well, they're always your left endpoint, your a. So that's 0 plus I times delta x. So that just simplifies to like 3i over n. Okay. And then we go throw this in the definition. So integral 0 to 3 of x squared plus or minus 6x. That'll be the limit as n goes to infinity. Okay, so first let's just write it down generically. It would be delta x, and then we'll swap in what we have. Right, so it's roughly like this, right? It's the limit as n goes to infinity of delta x. And our delta x was 3 over n, so we would put 3 over n here. And our right endpoints were just 3i over n. So let's, okay, but now we have to, actually evaluate this part. Like, what is f with 3i over n plugged in? Well, what it is, so this part all stays the same. And our f is here, right? And so I'm plugging 3i over n in for x. That'll give you 3i over n. That comes from plugging that into the x squared part, and then minus 6 times that. Okay, so we get something like this. And now our goal is to figure out, like, what is this limit actually equal to? And if you came to the exam review, we did do one sort of like this. We didn't write it down from an integral, but the idea is you work on the inside part first. So you try to get this to something that doesn't involve a sum anymore, because we don't really know how to deal with limits and sums together. And to do that, we have to use our summation formulas we learned before. So we want to get it down to like a sum of I, a sum of I squared, a sum of I cubed, or a sum of a constant. And so that's what we try to do, is we try to simplify this down. Okay, so you would do something like, let's leave the 3 over n. We would break this up into, so an important point that a common mistake that people make is you have to make sure that you understand there's like implied parentheses here. So when you split this into two sums, really the 3 over n goes on both pieces. And let's just square this out. This will be 9i squared over n squared. Right, so what I'm saying is this will go on both. So I get another 3 over n on the second term. Times 18 I over n. So we can split it up like that. And then we can pull all the constants out of the sums. So if we do that, that would, so basically what I'm doing is I'm taking this part out, right? You can pull anything through the summation that doesn't involve I. So I can pull the 9 over n squared part out, and that'll result in, 9 times 3 is 27, and then I'll have an n cubed. Now I just have the summation of I squared, which is kind of what I was going for. And then if we do the same thing in the second term, 18 times 3, what's that? That's 54 maybe. 54 over n squared times the summation of I. Just I. And now we know these things have formulas, right? This thing has a formula, and this thing has a formula. Right, so we can go ahead and replace them with the formulas. Okay. So the one for I squared was, it's the top number times the top number plus 1 times 2 times the top number plus 1 all over 6. And the second one gets replaced by just the top number plus 1 over 2. So these were the summation formulas we learned, right? This got replaced with this got replaced with this. And now these are just numbers that depend on n. So let's think about this. So let's do maybe a little bit more simplification. What's the best way to say this? So I'm going to rearrange this first term a little bit. Doesn't really matter what order you write it in on top. And now on top bottom we'll have an n cubed. Or maybe we should write it like. Then the second part, we'll have 27 n squared plus 1, or plus n over n squared. Okay. And so if you remember, when you're taking limits, you can take the limits of each part individually, as long as they're not like infinity or anything. And so in the second limit is probably the easier one. The second one is probably easier. You'll see that, if you think of like the n's as x's, this is exactly a limit at infinity. And you'll notice that these powers are the same, right? They both have power 2, and that's both the largest power on top and bottom. So that means the limit of this part will just be 1, right? It's the ratio of their coefficients, which are both just 1s. And you can do a similar thing here, right? In the first term. So if you look at this numerator, and you imagine you were to actually just multiply this out and think about what the terms would be. Well, the largest power of n would come from when all the n's get multiplied, right? It would be these three hitting each other. And so then that term would be a 2n cubed. Then you'd have some garbage times n squared plus some garbage times n plus some constant term, right? That you'd have to figure out. But the important point here is we don't have to figure all that out. All we have to notice is that the highest power on top and bottom is still a cube. And the coefficient of the top one will be 2. And the bottom one will be 1. Okay, so putting that all together, what we can say is that we'll take the limit of 27 over 6. The limit of this bit is just 2 over 1. Then we have our, sorry, we're doing the limit, so we don't need the limit anymore. So we had 27, then the limit of that other piece was just 1 over 1, which is 1. And that will give us our answer. So let's see, 27 over 6, that's 9 halves, cancel a 2, so that's 9. So this looks like it's minus 18, possibly. Okay. So yeah, if I ask you to compute an integral from the definition, this is essentially what I mean. And the steps are, you write down the definition. So you write down with everything plugged in. Then you simplify it down until you can get the sums of the form where we know the formulas for it. So like things with just a summation of I squared, I cubed, or a constant. Use the formulas, and then think about limits at infinity and the properties of limit to get the final answer. All right, so any questions here? Okay, well, I want you to spend a few minutes making sure you can do one yourself. So spend a few minutes and try computing this one from the definition. So write down the definition involving a limit of a sum, and then see if you can simplify it down to the correct answer. Okay, so let's do this one a little bit more quickly. So we would first write down the definition, which says it's the limit as n goes to infinity of this so delta x here is what? It's 3 minus 0 over n, so 3 over n. So that would go in front. And then we're going to take f at right endpoints, which will be 0 plus 3i over n. But f here is really just x cubed, so it's really just 3i over n cubed. So that would be the definition here. Okay, and then you would try to simplify it down to just having a sum of probably I cubed here. So that would mean, if you do this part, this will be 27 I cubed. So if we throw that in here, we pull, so if we pull that out of the sum, things are getting a little crooked. You can get it down to something that looks like this. Okay, and then we know that there's a formula. You might have to look it up again for I cubed, right? Remember, it's n plus 1. It's like the other formula, but it's squared. Okay, so if we use that here, so let's see, 3 times 27, that's 81 over n to the 4th. We're replacing this, and now that's just exactly what it says, n plus 1 over 2 squared. Okay, so now our limit doesn't involve any sums. Now we can start thinking about what the limit itself is. So maybe the easiest way to see it is something like, on top, or if we just square everything out, you get something like this. And if we're thinking about limits, right, we can rearrange this. We can swap the 4 with the n to the 4th. If you think about this numerator and you were to distribute it all out, right, multiply everything out, the n plus 1 squared term would have an n squared term in it. And so if you think about like this times this, that would end up with an n to the 4th. Like this times this would be n to the 4th. Right, because the n gets squared, and then times n squared will be an n to the 4th, and it's the coefficient in front of it will be 1, right? And then it'll have some other stuff after it, right? But nothing else will have an n to the 4th term, and so the largest power on top, you could just multiply it all out if you're really uncertain. But they have the same power on top or bottom, top and bottom, and their coefficients are both 1, so this whole limit, this whole thing just goes to 1 in the limit. So when we evaluate the limit, it's just 81 over 4 times 1 over 1. So it's just 81 over 4. Okay. So you guys start to see the idea. You can imagine if you threw like a really complicated function in here, like something that involved like sines and cosines and square roots and tangents, this would be a complete nightmare, right? Because we don't have formulas for things that involve like sines and cosines. So we're going to have to work on a way to do this without using just the definition. And we'll come to that maybe at the end of today. Yeah, other than that, does anybody have questions about this sort of stuff? Okay, so here's another example, but this one is sort of thinking of it in the backwards direction. So now we're given this limit of a something, and we want to see, like, is there some integral that it's equal to? So the question here is, can we write this as a definite integral? And so what we have to figure out is we have to figure out, what goes here, and then what goes in the middle, right? Maybe we can make that a different color. Right, so we have kind of three pieces of information we have to decide here, right? And maybe it can help to compare this sort of side by side, right? So the definition of the integral of a to b of a sum function is defined to be, the thing we just wrote down like 3 times. Delta x times the sum of the heights of the rectangles at right endpoints. So that would be f with a plus I times delta x over, this, right? Okay, and so yeah, basically the idea is you want to compare these and match up these 3 pieces of information that I highlighted over here on the right. And, you maybe had sort of a loss of where to start, but one thing I can point out that is helpful is it's usually the easiest thing to identify is this part here, the b minus a over n. So in this formula, the only thing that looks like a number over n is this part here, right? And here it appears inside the summation instead of outside, but that's okay because we can move it. It doesn't involve I, right? So what does that tell us? That tells us that, b minus a over n has to be 3 over n. So that means the b minus a is 3, right? These two things have to be equal. So that means the width of our interval is 3. Okay, so that means whatever I put on the bottom here, the top has to be 3 more. And it turns out there's actually infinitely many answers to this, sort of like when we were doing the summation stuff. So the other we have to choose a number for the top and bottom, and we know like whatever we put on the bottom, the top has to be 3 more. Now let's think about, the function part. So kind of the tricky part here is what is a? And It really comes from looking at this remaining part. So in this part, how do we make this match this? That's probably not a good way to do that. How do we make this match this? Which A and which B do we choose and which F? Well, it looks pretty clear to me that it has to be like, you know, F probably has to be something like 1 over something, right? And then we just have to basically start guessing A's and B's. And well, maybe we just try 1 over X. Can we make that work? And because sometimes the one thing you just have to do in math is you have to try something. If it doesn't work, you can see why it doesn't work and then alter your guess to find something that works better and kind of repeat the process to get closer and closer. So maybe we just try 1 over X. So if I had 1 over X, whatever I plug in for X has to end up being 1 plus 3i over n. So that would tell me that A should be 1 from the 1 here. And so if A is 1, B has to be 3 larger, so B has to be 4. And if you write this out, sorry, what am I saying here? And if you just end up trying that, you'll see that this is indeed a valid answer. Like the integral from 1 to 4 of 1 over x dx will work out to be this summation thing. Another thing you could have done is you could have said, well, maybe I want to start it at 0 for some reason. Maybe I want my A to be 0. If your A has to be 0, you know, B still has to be 3 larger. So B would have to be 3. But then you have to change your function, right? And it turns out the way you would have to change it is you'd have to change it to be 1 over x. Because if you think about it, right, because A now is 0, so there would be no 1 to compensate it, so I have to add the 1 here. But B minus A over n would still be 3 over n, and so it would work again. So there are many ways to do this. Okay, and it is a bit of guessing and checking. So yeah, either one of these would be correct, and there's actually infinitely many more answers. Okay. So these are good practice. It really makes you try to think through everything. Okay, so any questions about that one? I'm not going to spend too much time on that sort of thing because it's not that commonly used. All right, so we're going to now move on to like talking about, you know, easier ways to calculate integrals instead of these big limits of some things which are like really annoying. You know, it's very similar to like, you know, when we had derivatives, we learned the limit definition way, but then eventually we turned out there were easier ways to do it. I mean, it's all still based on the limit stuff, but there were easier ways eventually. We had all the formulas. And it's the same way with integrals, though integrals tend to be a little harder in general. So kind of the first step in this is, you know, just like derivatives had certain properties, so do integrals. And here are the simplest of them. So really the ones I would want you to know are 1 through 3. 4 and 5 are still good. I kind of put them in there for completeness, but I would like you to concentrate on understanding 1 through 3 the most. And you can find these on the summary sheet. I forget if I've posted it yet, but I'll make sure it's up there after class. And so what do these say? It says if I'm trying to calculate an area, well, let's look at number 1 first. So it says if I'm trying to calculate the area of 2 functions added, well, it's the area under the first plus the area under the second, right? And if you think about it, this really makes sense in terms of pictures of area. So, right, if you have like, what's the best way? So say the green thing is g of x, the red thing is f of x. Then what would f plus g of x be? Well, it would be what you would get from adding them. So it would be something more up here. And here, because g is roughly flat, it would just kind of shift f up. And so what it's saying is, if you take this area, and then you stack on top of it this area, if it was to scale, that would be the same as this part. And if you add them together, they just kind of stack. So yeah, the moral of the story is you can do what we do with derivatives and limits and sums. If you have the integral of 2 things added or subtracted, you can break that into 2 simpler integrals and do them separately. But that only works for addition and subtraction, right? It won't work for multiplication or division. And also similar to derivatives, limits, summations, if you have a number, you can pull the number outside, as long as it doesn't involve an x, basically, or really the bounds either, but it shouldn't. But yeah, if you have a number sitting in an area, in an integral, you can pull it out. Okay. Number 2 says basically that, if you just think about it in terms of areas, if you have one function f, and then you have another function, let's see, g, which is always bigger, and then you ask about areas, well, which of these 2 areas is going to be bigger, the green area or the red area? Well, it's clearly going to be the green area, right? And so that's the idea is just because the function is higher in g, so if you know that g is always higher, then the area will also always be bigger. It's just sort of a fancy way of saying that. And then the third one, which also gets used quite a bit, is saying, like, if I take the integral, so sort of the way you should read this is, you have from a to c, then from c to b, right? And that's the same as the area from just a to b. Okay, so in terms of pictures, let's see, maybe we can just draw it down here. It's saying if you take the area, so you have some function f, and then you have 3 points now. Let's say you have a C, and a B. So I didn't put these in alphabetical order. It feels a little weird. But it's saying if you take the area under F between A and C, that's this term. That would be this term. And I add to it the area between C and B, that would be this area. That would be this term. Well, it says that's just the same as doing, this entire area. Right, so, from a picture, this is something that clearly has to happen. But the kind of the key thing you can recognize about when this is useful is when you have a top and a bottom number that match, right? So you have a C here on both. That usually kind of tells you that this rule is involved somehow. Okay, so these are kind of the properties of the integrals I'm going to expect you to know. Actually, there's a couple more that aren't listed here that I should mention. So yeah, we should definitely mention these. So other rules. These are really consequences of the other ones, but they come up so often that it's just helpful to know. So the first one is if I ask about an area from one number to the same number itself. Well, this is just always, it's basically a convention or a definition, and then also a consequence of the definition that it's just zero, right? Because there's no width. It's sort of like if you ask, like, what's the area of a rectangle that has zero width? And we usually call that zero, right? So if you have the same number on top and bottom, the answer is always zero. You don't have to think any further. Okay, and then the other kind of one is, I guess we don't need dots here. If you have an integral, and for some reason you want to switch the bounds, switch the order, you want to put the b on bottom instead of on top, you can do that, but we just define it to be the negative. It's sort of, basically what it's saying is, whenever we calculate areas, we always calculate them from left to right. We call going from left to right positive if it's above. And so if you go the other way, it's more of a convention that we use, that we call that negative. Just because everything works out so nicely if you make that definition. Okay, so the moral of the story is if you swap these things, right? If you swap these, you have to add a negative. Okay, so an integral from a number to the same number is zero, and if you swap the bounds on an integral, you have to add a negative. Okay, those are the other rules. Okay, so let's play with these a little bit in some examples. Okay, suppose we know that the area under f between 1 and 3 is 12, and so we don't know what the function itself is, but we do know about its area, and we know, what is this, 1 to 3 of g of x, the area under g is -4, then the question is, what is so I'm going to ask two things. Okay, so here's the question. So we're given information about two areas here, and we're asked about two other areas that are combinations of our G and F, right? Okay, so the basic idea here is, like, if we look at this first one, well, there was a rule that says we can split this into two integrals, and you always keep the bounds the same when you do that. Maybe let's do this in a different color. Integral 1 to 3 of 4f of x dx. So the dx, remember, you should always include it. It just tells you where the integral ends and also which variable you're integrating with. But and then you have another one. So you can split this into two things across the minus. Then you can pull out the 4, just like we do with limits and sums and derivatives. Okay, so you can simplify it down. And the point, or the reason we did this is because these are the things that were given, right? We were given this thing, the integral of the area under f between 1 and 3. So that part is just 12. And this other one is minus 4. So altogether, it's 4 times 12 plus 4, right? Because we have minus and negative, so that's what? 48, 52, if anybody cares. Okay. And in the second version, well, the idea is the same. We want to get these down to things that match the information that's given. And we see that these are in the wrong order, right? 3 is on the bottom here, where in the top ones, they're in the reverse order. So we have to use that other property where if we switch them, we have to add a negative. Or maybe let's do this in a different color again. So we have to add this extra negative. Integral of 1 to 3. Integral 1 to 3. Everything else stays the same. Then we would break it up again. So we'd have minus integral of 1 to 3 of g of x. But you remember that there's like implied parentheses here, right? So really you have to make sure this negative goes on both things. Okay, and now we know that the g of x one was minus 4 and the other one was 12. So this would be minus 4 minus, or was it negative 4? I can't remember. So you get something like this. So let's see, that would be minus 16. Looks like it would be 16. Okay. So any questions about that one? It all works very similar to what we've done before, so maybe it's not too much new. Okay, so let's do a one that's a little bit different then. Okay, so now suppose this time instead you know that this is true. That this area is 10. And you also know, let's see, can I put it here? The integral from 5 to 8 to 5 of the same function. This is equal to 9. So I know these two areas. Then the question is, what is integral from 5. Sorry, that's not what I want. I want the integral from 3 to 5. Okay. So this is all three of these things are telling us things about areas under F. So if you think about this in a picture, right? You know, we don't know what the function f looks like, but we can just make up any old one. It doesn't really matter what it looks like. And then there's these three numbers here, right? There's 3, there's 5, and then there's 8. And this first one, this integral from 3 to 8, that's telling us this area. And then if we look at another one, if we look at the second one, that's telling us about this area. Or no, it's not. It's telling us the other one. It's telling us this one. And then we're being asked about this other area, right? So to get the pink area, you have to take the green area, which is the whole thing, and subtract off the part you don't want, which is the blue. So pink will be green minus blue, right? So pink is this thing. And so that's exactly the answer. We're really using that additive property before, right? So there's a couple ways to think about this. You could just look at the picture, or you could recognize that, you know, the integral from 3 to 5 plus the integral from 5 to 8 has to be the entire thing from 3 to 8. And so the part we want was from 3 to 5. If we solve for that, it'll tell us what we just saw from the picture. It'll be the entire area from 3 to 8 minus the area from the blue part from 5 to 8. And we know both of these numbers, right? So this will be, so from 3 to 8 was 10, from 5 to 8 was 9. So the part that's left over is 1. Okay, so that sort of thing can be useful as well when you're, you know, either splitting up or combining these integrals. You can also do them like from left to right. All right, so any questions about this? I think we're going to stop there for today, and we'll start the fundamental theorem of calculus on Monday. I feel like we've had a busy week. So yeah, I hope you guys have a great weekend, and I'll see you on Monday.